Imagine you're trying to teach a neural network to sort a list of numbers. You'd think the order in which you hand the network those numbers shouldn't matter much, right? After all, a set is a set. But it turns out this question of whether input and output ordering matters for sequence models has some surprisingly deep implications. And it's the central puzzle that Oriol Vinyals, Sami Bengio, and Manjunath Kudla from Google Brain set out to untangle. Let's set the stage. The Sequence-to-Sequence framework, or Seq2Seq, has become one of the most successful patterns in deep learning. The recipe is simple. You take a recurrent neural network, usually a long short-term memory network or LSTM, and use it to read an input sequence token by token, compressing it into a hidden state. Then you use another LSTM to decode that hidden state into an output sequence, again token by token. The magic comes from the chain rule of probability, which lets you decompose the joint probability of a whole sequence into a product of conditional probabilities at each step, without having to make any independence assumptions. This works beautifully for machine translation, image captioning, parsing, speech recognition, and more. But here's the wrinkle. What if your data isn't naturally a sequence? What if you want to feed in a set of unordered objects, like a collection of points in the plane, or output a set of detected items where there's no canonical order? The Seq2Seq framework demands an order, so you have to pick one, somewhat arbitrarily. The author's first big claim is that this arbitrary choice matters enormously in practice, even though in theory a sufficiently powerful model shouldn't care. Think of it like teaching someone arithmetic. Mathematically, 2 plus 3 plus 4 equals 9, no matter the order you add them in. But if you're a learner just starting out, certain orderings genuinely make the problem easier to learn. The evidence for this is striking. In the original Seq2Seq machine translation paper, simply reversing the input English sentence gave a 5-point improvement in BLEU score, closing the gap with heavily engineered state-of-the-art systems. For constituency parsing, reversing the input gave half a point of F1. For computing convex hulls of point sets, pre-sorting points by angle changed the asymptotic difficulty of the problem from order n log n to linear, yielding up to 10% absolute accuracy improvements. So order matters, and the authors argue this is fundamentally because of the non-convex optimization landscape that gradient descent has to navigate. Some orderings provide better inductive bias and gradient flow. Now the deeper question, if order matters, but we're given a true set with no natural order, what do we do? The authors propose an architecture called read, process, write. The reading block takes each element of the input set and embeds it through a small neural network, producing a memory vector for each element. The processing block is where the interesting work happens. It's an LSTM that takes no inputs and produces no outputs. It just sits there, evolving its hidden state over a fixed number of computation steps. At each step, it uses its current state as a query into the memory vectors via a content-based attention mechanism. It computes a score between the query and each memory, normalizes those scores with a softmax to get attention weights, reads out a weighted combination of the memories, and concatenates that readout with its query to update its state. After several such steps, the final hidden state is an embedding of the whole set that, crucially, is invariant to the order in which the memories were laid down. Permuting the inputs permutes the memories, but leaves the attention readouts unchanged. Finally, the writing block is a pointer network that points back at elements of the input set to produce the output, optionally with its own attention glimpse before each pointer step. The sorting experiments validate the approach nicely. On sorting 5 random floats, a vanilla pointer network with an LSTM encoder gets about 81% accuracy, but read process write with 10 processing steps and glimpses reaches 94%. On sorting 15 numbers, where the vanilla approach essentially fails at 0%, the new architecture gets to 10%. More processing steps reliably help, and adding the glimpse attention before pointing roughly doubles accuracy in the hardest cases. The key insight is that the number of processing steps decouples the computation budget from the size of the input, letting the model iteratively refine its understanding of the set. For the output side, the authors face a symmetric problem. When you have to produce a set, you're forced to pick an order to apply the chain rule, and different orders can be dramatically easier or harder to learn. Their experiments on the Penn Treebank language modeling task show that reversing a sentence 3 words at a time, which scrambles natural n-gram structure, hurts perplexity by 10 points. On parsing, switching from depth first to breadth first tree traversal drops F1 from 89.5 to 81.5%. On a synthetic graphical model task with a star structure, training is much easier if the root variable is generated first rather than last, especially with limited data. Their proposed fix is to let the model learn its preferred ordering during training. Concretely, instead of fixing a target ordering, they search over orderings to find one that maximizes likelihood under the current model, then take a gradient step on that ordering. To avoid getting stuck in whatever ordering the random initialization happened to favor, they first pre-train for 1,000 steps with orderings sampled uniformly at random, and then switch to sampling orderings proportional to the model's own probability, which they can do efficiently with ancestral sampling in just one model evaluation rather than n factorial. On a 5-gram language modeling toy task, this procedure successfully discovers the natural left-to-right ordering even when all 120 possible orderings appear in the training data. There are real limitations here. The search over orderings procedure is somewhat heuristic and only demonstrated on small problems where n is 5. Scaling this to outputs with hundreds of elements is unclear. The theoretical claim that any order should work given a powerful enough model is not really resolved. Rather, the empirical reality of non-convex optimization keeps biting. And the read-process-write architecture, while elegant, still requires you to choose the number of processing steps as a hyperparameter, and longer set inputs may need more steps to be properly digested. Now let's walk through some questions you might have after hearing all of this. You might be wondering why an LSTM, which is a universal approximator over sequences, can't just learn to ignore order if order shouldn't matter. The answer is that universality is a statement about what's expressible in the limit, not about what's learnable from finite data with gradient descent on a non-convex objective. The LSTM has the capacity to be order invariant, but the optimization landscape doesn't make that easy to find. Some orderings put the relevant information closer to where the decoder needs it, or create simpler dependency patterns that gradients can more easily propagate through. Another natural question is what makes the attention mechanism in the processing block truly permutation-invariant? The trick is that attention computes a score between the query and each memory independently, then aggregates them through a weighted sum. Summation is commutative, so if you shuffle the memories, you shuffle the terms in the sum but get the same total. Contrast this with feeding the set through an LSTM, where each step's output depends on the running hidden state, which depends on the order you processed elements in. You might also ask why they don't just train with data augmentation, randomly permuting outputs to force the model to be order invariant. They tried something like this for sorting and found it actually hurt. The model had to spread probability mass over all n factorial valid orderings, making it statistically inefficient and slow to converge. Restricting the equivalence class of valid outputs to a single canonical ordering concentrates the learning signal, which is why they instead try to find one good ordering rather than treating all orderings as equivalent. Now, how does this connect to large-scale recommendation systems? The set handling problem shows up everywhere in production recommenders. A user's recent interaction history, the items in their cart, the candidate pool returned by retrieval, the user's social graph neighbors, all of these are fundamentally sets, not sequences, yet most production systems hack in some arbitrary ordering, often by recency or by ID. The read-process-write pattern offers a principled alternative for user modeling, where you embed each historical interaction independently, then run several rounds of self-attention over them to produce a permutation-invariant user representation. This is essentially the conceptual seed that grew into the deep interest networks and transformer-based user encoders that now power ranking at companies like Alibaba, Pinterest, and Meta. The output ordering insight is equally practical for re-ranking and slate generation. When you're producing a ranked list of, say, 10 items to show a user, you're really generating a set with positional structure, and the order in which you decode matters for both diversity and learning efficiency. The idea of letting the model discover its preferred decoding order, or of carefully engineering it based on signals like predicted relevance, can meaningfully improve slate-level metrics. And the attention-based set encoder is friendly to real-time serving because the processing steps can be a small fixed number independent of how long the user's history is, giving you predictable latency even for power users with thousands of interactions.